Plastic deformation is a common phenomenon in many industrial applications. In this tutorial, we will model the plastic deformation of a metal tube using COMSOL Multiphysics. You will learn how to use the solid mechanics interface together with appropriate boundary conditions, including contact, symmetry, prescribed displacement, and fixed constraints. We will also discuss why form assembly must be used when modeling separate parts that interact through contact. In addition, we will create a structured mesh for improved solution quality and use a 2D mirror dataset to visualize the complete geometry from a symmetric model. Hello, I'm Armin. Before we begin the simulation setup, let's take a closer look at the model and the underlying concepts. Elasticity and plasticity are fundamental concepts in metal deformation. When the deformation is small, a metal returns to its original shape after the applied load is removed. However, when the deformation exceeds a certain limit, such as in processes like deep drawing, part of the deformation becomes permanent, and the material no longer fully recovers its original shape. This behavior defines the distinction between the elastic and plastic regions. In technical terms, a material is considered elastic when it returns to its original size and shape after the applied load is removed. Two key parameters characterize elastic behavior: the elastic modulus and the elastic limit. A high elastic modulus indicates a material that is difficult to deform. The elastic limit is the stress level beyond which the material no longer behaves elastically and permanent deformation begins to occur. When the applied stress exceeds the elastic limit, typically around 1% strain, the material enters the plastic region. In this regime, deformation becomes irreversible, meaning the material does not return to its original shape and size after unloading. For ductile materials such as metals, once the stress exceeds the elastic limit, the stress-strain response changes significantly. The material undergoes progressive permanent deformation as it approaches failure. This model represents a 1 meter long metal tube, simplified using a 2D plane strain assumption. Linear plasticity is included to capture irreversible deformation once yielding occurs. To reduce computational cost, only half of the geometry is modeled by applying a symmetry condition along the center line. The tube is compressed between two rigid jaws. The upper jaw is defined as a rigid domain with a prescribed displacement to impose the loading, while the lower jaw is fully fixed to provide support. The model is discretized using a structured mesh to ensure numerical stability and accuracy in the contact region. A stationary solver is used together with an auxiliary sweep, allowing us to simulate both the loading and unloading stages of the compression process in a controlled sequence. The first result shows the evolution of von Mises stress during the compression stage, where the highest stresses develop in the contact region between the tube and the rigid jaws. The second result presents the stress state after unloading, highlighting the residual stresses that remain in the material due to plastic deformation. The explanation is sufficient. Let's get started. I'll start by clicking on Model Wizard. Since this geometry is suitable for a plane strain assumption, I select 2D space. In the Select Physics step, I set up a structural analysis. I expand Structural Mechanics and select Solid Mechanics, then click Add. As shown, the Solid Mechanics interface is now listed under Added Physics Interface. In the Review Physics Interface section, the dependent variable is defined as displacement, which is the primary unknown in solid mechanics. I proceed by clicking on Study. In the Select Study step, the solver type is defined. I choose a stationary study. This can also be set to time-dependent if required, but here I proceed with stationary, then click Done. Now we move on to the geometry definition. First, we create two circles to form a tube-like structure. Before starting, I switch the length unit from meter to millimeter, since the geometry is relatively small. Next, I right-click on Geometry 1 and select Circle. This can also be done from the Geometry tab or the Sketch interface. Now I set the radius to 10 millimeters. Since I only need half of the circle, I set the sector angle to 180 degrees, then click Build All Objects. After that, I rotate the geometry by 90 degrees counterclockwise and build it again. Now I create the second circle. The fastest way is to duplicate the first circle. I right-click Circle 1 and select Duplicate from Context menu, then change the radius from 10 millimeters to 9 millimeters and build the geometry. This method is much more efficient than creating a new circle from scratch. Finally, I keep only the annular region representing the tube thickness. I go to the Geometry tab, expand Boolean and Partition, and select Difference. The larger circle is assigned as the object to add, and the smaller circle as the object to subtract. After clicking Build All Objects, the annular shell is created. Now, let's create the two rectangular jaws on the upper and lower sides of the tube. I navigate to the Geometry tab and select Rectangle. Alternatively, I can right-click on Geometry 1 and select Rectangle from the Context menu. I'll click on Rectangle 1 to define the dimensions. Since I only need half of the jaw geometry, I set the width to 9 millimeters and the height to 1 millimeter in the Settings panel. Then, I click Build All Objects. Next, I adjust the position so the jaw is located below the tube. In the Position section, I enter -9 millimeters for the X coordinate and -11 millimeters for the Y coordinate. Then click Build All. As shown, the lower jaw is now positioned beneath the tube. Now it is time to create the upper jaw. Instead of creating a new rectangle from scratch, I simply right-click on the existing rectangle and select Duplicate. I only change the Y position to 10 millimeters, then click Build All Objects. This duplication approach is much faster and more efficient. At this point, the geometry consists of 3 separate parts. This geometry should eventually be converted from form union to form assembly, because the model consists of 3 separate parts, while form union merges all domains together. However, for now I keep the default settings, so we can observe their effect on the simulation. Next, we define the material properties. I right-click on Materials and select Add Material from Library. In the built-in material library, COMSOL provides many common engineering materials. Here, I choose Structural Steel and click Add to Component. Structural steel already includes a wide range of material properties, including several nonlinear parameters such as plasticity, hardening behavior, and strength-related properties, so there is no need to define an additional material manually. Before adding the boundary conditions and configuring the solid mechanics interface, I'd like to define the contact conditions between the 2 jaws and the tube. At the moment, the geometry is still created using the union operation, so the domains are already bonded together. However, I include this setup for later use when switching to form assembly. I right-click on Definitions, then from Pairs, I select Contact Pair. When defining a contact pair, we need to specify the source and destination boundaries. In general, the source boundary is assigned to the stiffer side or the body expected to act as the master surface. Here, I select the 2 jaws as the source boundaries, since later they will behave as rigid components, while the tube will remain deformable. For the destination boundaries, I select the contact surfaces on the tube. Next, let's create the second contact pair. I right-click on Definitions again, go to Pairs, and select Contact Pair once more. I choose the other jaw as the source boundary, and then select the corresponding surface of the tube as the destination boundary. As soon as the contact pairs are created, COMSOL automatically adds the corresponding contact feature under the solid mechanics interface. Now, let's continue with the boundary conditions and configure the solid mechanics settings. I click on Solid Mechanics, and in the Settings panel, under 2D Approximation, we can see that plane strain is selected by default. I keep this option unchanged because the tube depth is much larger than its radius, which makes the plane strain assumption appropriate for this model. We also need to specify the out-of-plane thickness. In this example, I keep the default value of 1 meter, which is sufficient for the current setup. Depending on the actual geometry and loading conditions, this value can be adjusted. Now, let's define the boundary conditions. Since I only modeled half of the geometry, I need to apply a symmetry boundary condition. I go to the Physics tab, expand Boundaries, and select Symmetry. Then, I select all of the edges along the right side of the model. Everything looks correct. Next, we need to fix the lower jaw. The bottom jaw is assumed to be fully fixed and rigid. To define this, I expand the domain section and select Fixed Constraint. A fixed constraint defines the domain as a rigid support with negligible deformation. I select the lower jaw domain, and now the bottom jaw is fully constrained. We also need to define the upper jaw as a rigid body. However, unlike the lower jaw, this jaw moves downward slowly to compress the tube. For this, I go to the domain section again and select Prescribed Displacement. Then, I select the upper jaw domain. Even though these parts behave as rigid bodies, the material still needs to be assigned. In the Settings panel, I set the Y direction displacement to Prescribed and define the value as minus 0.002 meters, which corresponds to a 2 millimeter downward compression. To prevent lateral motion, I also constrain the displacement in the X direction. At this stage, the boundary conditions and rigid body definitions are fully configured, and the setup looks good. The next step is generating the mesh. I click on Mesh 1 and then select Build All to preview the initial mesh. There are two issues with this mesh. First, the jaws are modeled as rigid bodies, so there is no need to generate a large number of elements in those regions. Second, the mesh inside the tube is too coarse for an accurate structural analysis. To create a more structured mesh, I use a mapped mesh. I right-click on Mesh 1 and select Mapped. I keep the default settings because I want the mapped mesh to be applied to the entire geometry. Then, I click Build All. As you can see, this mesh is much more suitable for the current model. Next, I want to refine the mesh distribution. Since the jaws are rigid and do not experience stress or strain gradients, I only need a single element through those regions. To do this, I right-click on the mapped node and select Distribution. Then, I select the edges of the upper and lower jaws. In the settings, I specify one element and click Build All. The mesh now looks much cleaner and more efficient. Now, let's improve the mesh quality for the tube. I right-click on the mapped mesh again and add another distribution node. This time I select the tube edges. I set the number of elements to 8 and rebuild the mesh. As shown, the element distribution is now much better. However, I would like to apply a finer mesh near the upper and lower contact regions, while keeping a coarser mesh near the center. At the moment, the distribution is still uniform. To achieve this, I change the distribution type to predefined. I keep the number of elements at 8, set the element ratio to 3, and click Build All. At first, the refinement is applied only to the upper side. To make the mesh symmetric, I enable symmetric distribution and rebuild the mesh again. Now both the upper and lower sides of the tube have a finer mesh compared to the center region, which is more appropriate for capturing the contact stresses. Finally, I refine the overall element size. I go to the Size node and change the predefined mesh setting to Extremely Fine, then click Build All. As you can see, the mesh quality is now significantly improved, and the model setup looks good so far. Now, let's solve the model and evaluate the results. I click on Study 1 and select Compute to start the simulation. The solution completes successfully without any convergence issues, and the resulting stress contour distribution looks physically reasonable, especially around the jaws and in the middle region of the tube, where the bending moment produces higher stress concentrations. The next step is to add plasticity to the model. The implementation itself is relatively straightforward, although the underlying theory is much more advanced and likely familiar to many of you. To add plasticity, I right-click on Linear Elastic Material 1, and from the Context menu, I select Plasticity. Inside the plasticity settings, several constitutive models are available. For the isotropic hardening model, the default option is linear hardening. However, other models, such as the Johnson-Cook and hardening function models, are also available and are widely used in industrial applications involving nonlinear material behavior. For this tutorial, I keep the default settings unchanged. The kinematic hardening model includes the Bauschinger effect in the material response and therefore requires additional material parameters. For this example, I will leave the default settings unchanged, since the main objective here is simply to introduce the plasticity feature. In many cases, nonlinear simulations may fail to converge because plasticity introduces strong material nonlinearity, so do not worry if you encounter convergence issues. Now let's solve the model and see what happens. I return to Study 1 and click Compute. During the solution process, we can monitor the convergence plot to evaluate the nonlinear iterations. Fortunately, the solution converges successfully. Notice that the stress level decreases after enabling plasticity, and this behavior is physically reasonable. In a purely elastic material, the stress increases linearly with deformation without any yielding limit. However, once plasticity is included, part of the deformation becomes permanent, which prevents the stress from increasing indefinitely and leads to a more realistic stress distribution. Before continuing, I would like to visualize the complete geometry instead of only the half model. To do this, I go to Datasets, right-click on it, and select 2D Mirror from Context menu. The mirror position is already correct because the symmetry axis is aligned with the y-axis. After creating the mirrored dataset, I go to the stress plot settings and change the dataset from the Study 1 solution to the mirrored dataset, then click Plot. Now the full geometry is displayed. Next, let's discuss how to improve convergence control in nonlinear simulations. Since plasticity introduces strong material nonlinearity, it is often better to apply the load gradually using an auxiliary parameter or a load ramping function. To define this, I go to Definitions, right-click, and from Functions, I select Interpolation. Here, I define a simple ramp function. I start from the origin by entering the points 0, 0, and 1, which creates a linear ramp from 0 to full loading. As shown in the plot, the load increases gradually from 0 to 1. It is also good practice to define the units properly for the interpolation function. Since this function is dimensionless, I set the units to 1 for both the argument and the function value. Finally, I rename the function to load, which makes the setup easier to understand later in the simulation workflow. Everything looks good. Now we need to add a parameter to define the load argument. I go to Parameters 1 and create a new parameter. I name it para and set its initial value to 0. This parameter will be used as the argument of the load function. Let me show you how it works. Next, I go back to the prescribed displacement settings. In the prescribed displacement expression, I multiply 0.002 by the load function and pass para as the argument inside the parentheses. Also, notice that the load function name must be written with the first letter in uppercase. Finally, I add the meter unit inside square brackets to keep the expression dimensionally consistent. Everything looks correct. The next step is to define this parameter as an auxiliary sweep parameter. I go to Study 1, expand Study Extensions, and enable the auxiliary sweep option. Then, I click the plus sign to add the parameter. For the parameter values, I click on the Range button. The start value is set to 0, the step size to 0.05, and the stop value to 1. The start and stop values should match the range used in the interpolation function. Then, I click Replace. Now I click Compute. This approach is very effective for highly nonlinear simulations because the load is applied gradually, which significantly improves convergence stability. The solution completes successfully. In the convergence plot, we can see the solution progress for all parameter values. From the parameter list, we can move from 0 to 1, where a value of 1 corresponds to the full 2 mm displacement. Now, I want to unload the tube. This can easily be done by modifying the load function. I go back to the load interpolation function. In the table, I add a new point with an argument value of 2 and a function value of 0, then click plot. Now the load increases from 0 to 1 during compression, and then decreases back to 0 from 1 to 2, which creates a loading and unloading cycle. Finally, I go back to study 1 stationary and change the auxiliary sweep range so the end value goes from 1 to 2. After that, I click compute again. The solution is complete. Now, let's change the parameter value to 2 and click plot. As you can see, the upper jaw remains bonded to the tube during unloading, and the jaw pulls the tube upward. This behavior is not physically correct for a contact problem. That is why during the geometry creation step, I mentioned that we should use form assembly instead of form union. With form union, all parts are merged together, so the contact definition becomes unnecessary because the domains are already connected. To fix this, I go back to Geometry 1 and change form union to form assembly, then click Build All. Now the contact definitions become physically meaningful because the parts are separated and interact only through contact conditions. Next, I regenerate the mesh. Before solving again, it is a good idea to quickly recheck the boundary conditions and physics settings. Everything looks correct. Now, I go to Study 1 and click Compute. This time, the solution diverges. Let's investigate the reason. I click OK and open the stress plot. As shown, the jaw is now correctly separated from the tube during unloading, so the contact behavior is physically correct. However, the solver still fails to converge. The reason is that once the upper jaw separates from the tube becomes free to move in the y direction. In other words, the model loses stability because there is no constraint preventing rigid body motion. To fix this issue, the tube must be constrained in the y direction. I right-click on Solid Mechanics, then from the Context menu, I go to Points and select Prescribed Displacement. Next, I select the contact points between the lower jaw and the tube, and constrain the displacement in the y direction. Now this point can no longer move freely in the vertical direction, which removes the rigid body motion. Finally, I click Compute again. The solution now converges successfully without any issues. If we select the final parameter value, we can see that the upper jaw separates correctly from the tube during unloading, while the residual stress distribution remains consistent with the previous results. This tutorial covered the fundamentals of plasticity modeling, along with some common convergence and contact-related issues that may appear in nonlinear simulations. Thank you for watching. If you found this tutorial helpful, please like the video and subscribe to my channel for more COMSOL and ANSYS tutorials.